Okay, so here we're going to focus on something called a subspace. So as of now, we define this collection of vectors that we've had. All right, so we define this collection of vectors, of vector spaces. So what we're going to look at is, well, what if we had a subset of a vector space? Is the subset itself a vector space? All right, so here we want to define what is first of all, let's define a subspace. So definition, subspace. Subspace. All right, so we'll say W is a subspace of V. First, if W is a subset of V, W has the same addition and scalar multiplication. As V. And W itself is a vector space. Okay, so again, we have to check a couple things. First, that W must be a subset and a proper subset, so it's not empty. And the same operations must be used. All right, so for example, let's say here, let's define W to be the set of column vectors x3 such that the columns vectors satisfy this equation. All right. Okay, so here, and again, just what this means, we can kind of get a visual of what we're looking at here. So the column vectors are in R3, our Euclidean space, and that equation is the equation of a plane. And we can clearly see that it is, in fact, a subset. It lives within R3. All right, and really all that's looking for is that it's just not empty, so there is at least one ordered or one column vector that is part of this set. All right, so here W is a subset of R3, and really we could see here that plugging in, we can find values there, right? As we could solve how they're playing, that they do exist. All right, so what we want to do here is we want to know, well, is W itself, right? In other words, if you look at that plane, are all of those vectors, in this case ordered triples that are in that plane, are all those make up a vector space? And again, what makes it a vector space is that it satisfies these axioms. Okay, so we already have the addition and scalar multiplication that's been defined as our standard addition and multiplication for our ordered, or for our column vectors R3. So I'll check through. First, I want to check the closure properties. All right, so closure is additive closure and scalar closure, AC and SC. All right, so if I add two elements, are they in, not V, but in W here? Okay. So what that means is, let's say X, let's look at AC first. If X is my column vector X1, X2, X3, right? And it's an element of W, so it satisfies the above equation. and y is y1, y2, y3. Again, also an element of w, which means that those satisfy the equation above. So if I define x plus y the way I normally would, we have x1 plus y1, x2 plus y2, x3 plus y3. So now let me plug it into that equation. So I'll have 2x1 plus y1 plus or minus 5, excuse me, x2 plus y2 plus 7x3 plus y3 equals to 0. And really what I'm checking here is that is this true? Does it in fact equal to 0? And I guess here, why don't we, instead of getting ahead of myself here, let's start by simplifying. So if I distribute 2x1 plus 2y1 minus 5x2 minus 5y2 and then plus 7x3 plus 7y3. And again, rearranging these, right? So here we just have real numbers, so I can use the axioms of the real numbers. So I can kind of write them in any order I want. And we have 2x1 minus 5x2 plus 7x3 plus 2y1 minus 5y2 plus 7y3. Okay. And then here we see, since x1, x2, x3 are in the set W, then, and so is y1, y2, y3. So those satisfy the above equation. So each one of those is equal to 0. So we have shown here that x plus y is also in W. So it is closed under addition. So any vectors that are in W, adding them together will also be in W as well. Okay, so now let's look at a scalar closure. So again, we'll let alpha be any real number here. And let's let x, which again equals to x1, x2, x3, be an element of W. And now I want to look at alpha x, which is alpha x1, alpha x2, right? Our standard scalar multiplication operation. All right, and now I'll plug this in to my equation. So we have 2 times alpha x1 minus 5 alpha x2 plus 7 alpha x3 equals to, here I could factor out the alpha, and then we got 2x1 minus 5x2 plus 7x3. And we could see here, right, since the vector comes from W, this quantity is 0. So we get alpha times 0, which is simply 0. Okay, so what that tells me is that we have scalar closure. Okay, and I'm going to jump to the Z property. Does it contain the 0 vector? Well, if we let our 0 vector is 0, 0, 0, so plugging that into our equation, so we do in fact get the 0 vector here. Excuse me, the value of 0. So the 0 vector, we can conclude, is in W. All right, now, as I go through trying to, let's say if I were to continue, right, all of these have to be true, right? But if you look at the other remaining properties like commutativity, right, remember, all these vectors in W already live in V, right? So all these properties are going to apply, right? Like C, A. Now the 0, 1 wasn't a given, right? I did have to check that one. All right, I did have to check that the 0 was included in that subset. But all these other ones, the additive inverses, right? The scalar, the associativity, I already know it's closed under scalar. So the scalar multiplication, right? So this is going to follow DVA, DSA, and also the 1, right? Those aren't, those are still going to be in that subset, right? And I know they're going to hold because W itself already comes from a vector space. So here, I don't really need to go through testing all these properties right now, even though I know that it's a vector space if it satisfies all those properties, but I've already established the fact that R3, this is a vector space. All right, so all the vectors in W come from R3, so a lot of those properties hold, right? The ones that are really not assumed here are the closure under addition and the closure under scalar multiplication. All right, so those are the ones that I need to check, but the other ones actually are just inherited directly from R3. All right, so what we're going to see here is that the nice thing about working with a subspace, if it comes from a known vector space, is that I don't need to go through the tedious process of going through all 10 of these, right? Because a lot of these come directly from it, from the vector, from the set W coming from a vector space, right? Ones that are not directly inherited are the closure axioms, right? And the 0 vector. I do need to check those. Right, so in the next video, we'll introduce a formal theorem where it's going to tell me, well, if I know the subset lives in a vector space, in order to prove the subset itself is a vector space, I just need to focus on 4 particular properties, right? One, that it's not empty, right? That it contains vectors, right? And we can get that from just showing that the 0 vector is in there, right? Because that's also going to be necessary, right? Z must be in there.